Hello everyone, welcome to my video. In this video, we'll talk about example 3/190, which is part of section 3.10, angular momentum. So far, we have been using angular momentum for anything that is working on a smooth surface. When anything moving on a smooth surface, that means there's angular momentum conservation. Another example is in this case, in the space, right? In the space, there's no force acting in the tangential direction. For example, at point A, the tangential velocity is going this way, and there's no any force acting in this direction. That means your angular momentum will be conserved. However, point A is a special case. Okay, the tangential velocity is vertically going up and is making a moment arm perpendicular. However, when the velocity at any other point, point B for example, you can see that we can resolve this velocity into a radial and transverse component, or VR and V theta. VR is going through the rotating axis, which means this VR velocity is not going to create an angular moment with respect to the center. And V theta, on the other hand, there is a moment arm, will be creating an angular momentum with respect to the center. Remember, the only, as we saw in other examples, only the vertical component, in this case V theta, will be creating the angular momentum with respect to the sun, and that angular momentum is being conserved. So in this case, we have at point A, the closest approach of the sun, the comet has a velocity VA at 188,500 feet per second. Determine the radial and transverse component of its velocity at VB, at point B, where the radial distance from the sun is 75 times 10 to the 6 miles. Okay, there will be some unit conversion because in imperial unit we need feet, we need second. Okay, so first of all, we'll start with recognizing that radial component of the velocity is referring to V theta, and the transverse component is referring to VR. And it's already labeled for us, VR and V theta, which is part of the velocity at point B. Okay, it's not three velocities, it's one velocity, but just like real resolving forces, this velocity can be resolved or can be broken into VR and V theta. Okay, so we're given VA, feet per second. We're given RA, 50 times 10 to the 6 miles, and RB, 75 times 10 to the 6 miles. On the diagram, which is right here. Okay, this is our RA, and this is our RB, the distance. Okay, when we're calculating the angular momentum, we'll need the distance, we'll need the moment arm. So, if we are applying the conservation of angular momentum, we will have the angular momentum at point A equals to the angular momentum at point B. In this case, the comet RA VA equals to the same mass RB VB. Okay, and in this case, our VA is essentially the V theta at point A, and VB will be V theta at point B. Okay, let me just draw this. At point A, the velocity, this is our velocity A, VA, which is the same as VA, V theta at A. Because this is the tangential velocity, and it's already perpendicular with to the moment arm. Okay, and we'll sub in the number here. 50 times 10 to the 6 times the velocity equals to 75 times 10 to the 6 VB theta. Okay, we'll calculate our VB theta, 125,666.67 feet per second. This is our first answer. The radial component of the velocity at B. What about VR? How do we get VR? VR is also part of V. Okay, if we can somehow get the total velocity at point B, and we can use the Pythagorean theorem to get VR. In this case, although you would probably want to argue, okay, we were given R and theta, seems like there is R theta system here. However, we do not know anything else. We don't know the theta dot, we don't know the R dot. So we cannot use our existing knowledge regarding our theta system, the polar coordinate system. In this case, we'll use the energy conservation, right? From point A to point B. What's the potential energy? What's the kinetic energy? And in this case, we have the gravitational potential energy. And because this is in the space, the gravitational potential energy will use the gravitational law instead of just simply mgh, because this is way, the height is way above the surface. Given that, we'll use from A to B. We'll use energy conservation. Energy conservation will have kinetic energy at A plus potential energy at A equals to kinetic energy at B plus potential energy at B. Subbing number, 1/2 mVA squared is my kinetic energy, minus the potential energy that we're using the gravitational law is always minus G m sun and the m comet are A. If you forgot this part, you can take a look in previous sections. We talked about this. Okay, potential energy, when calculating potential energy for using the gravitational law, it's always the minus. And on the right hand side, 1/2 mVB squared minus G, the sun, m, and RB. And you'll see that the mass of the comet itself is going to be cancelled. Okay, now we'll keep going here. 1/2 VA squared minus 1/2 VB squared equals to G, the mass of the sun, 1/RA minus 1 over RB. And apparently you will need the mass of the sun. Okay, and this number can be found in table D/2. If this is in the exam or something, you'll be given this number. Okay, we'll be subbing the number here. I moved this 2 to the right-hand side. So I end up with VA squared on the left-hand side minus VB squared. On the right-hand side, I have this number 2 came from the left-hand side. 2 times the gravitation constant, G, in imperial unit, 3.439 times 10 to the minus 8 times 333,000 times 4.095 times 10 to the 23. Okay, let me just label something. This is G, the gravitational constant. This is the ratio mass of the sun over mass of the earth. And this is mass of the earth. These are all given in table. Let me write it down. Table D/2. As I said, these values will be given to you if this is in the exam. Okay, we're not done yet. We still need this part. 1 over RA minus 1 over RB. We'll have, so multiply 1 over 50 times 10 to the 6 minus 75 times 10 to the 6. And we'll do the conversion. Convert mile to feet. Divide by 5280. Okay, this is the last part is converting miles to feet. Is unit conversion in SI unit. Okay, all these, this is whole one single equation here. We'll be getting VB, the total velocity, which is this guy, equals to 153,915.48 feet per second. Now we can use this relationship, the right angle triangle, to find out what is our VR, the transverse velocity. Or you can think of this is the velocity is not creating any angular momentum with respect to the sun, with respect to the center. Therefore, VR squared equals to VB squared minus V theta squared. You'll be getting VR, the transverse velocity, 88,869.9 feet per second. This is our second answer. We got V theta on the previous page, and we got VR right now. Thank you for watching. I'll see you next time.